In the previous video, we talked about using contrast to set up a comparison of parameters, and specifically in our example, population means. But of course, we do not have access to parameters. We have to use statistics. We have to use observations in order to be able to estimate what those parameters might be. So let's turn our attention now to estimating a contrast. So here is the formula for estimating a contrast. You notice that we have a hat on psi, and we use hats over Greek letters to indicate that we are no longer talking about a parameter, but rather an estimate of a parameter. And what makes it an estimate of a parameter? We have a hat here on mu as well. So we're going to be using sample means instead of the population parameter means, which we don't have access to. So this is the same formula as what you saw back here, with the exception that we now have hats on top of our parameters, meaning that we are going to replace the parameters with statistics. Let's call in our studio and the R notebook that we've been using to look at the data that looks at the perception of risk for the different worldviews. And specifically, I've brought us here to the descriptive statistics that we calculated in an earlier video. And we're going to be focusing, of course, on the means here. So let's suppose that we wanted to compare the mean of the individualist to the mean of the egalitarian. That would be the 38.96 and the 24.92. So we write this as our contrast is between the mean of the individual being estimated, the individualist, and the mean of the egalitarian being estimated. And then, of course, for this, we can actually fill in the specific means. And so we had for individualist 38.96. Let's just call that 39. Obviously, I would want to leave more decimal points in if I was doing the actual calculation, but just since we're looking at this pedagogically, it'll be easier if we call it 39 and 25. So I have 39 minus 25, which would equal 14. So this would tell us that the individualist has a mean that is 14 greater than the egalitarian. But obviously what we're really interested in is what is this equal to, that is without the hats on it. So our 14 is our best estimate of what this is. It's our best guess, best single guess. Obviously, at some point, we're going to need to put a confidence interval on this so that we can actually put attach some sort of level of confidence to our estimation. We don't have any confidence in a particular single value, a single point estimate, even though this is our best guess. But by putting an interval around it, we can then talk about the degree of confidence we have. But we're starting here with just our single best guess. And of course, we could go ahead and do this for all of the pairwise comparisons. Let's do that within the R notebook. So let's scroll down here. Let me go ahead and just put in a code chunk. And I'm going to use our real quick way of getting all the means. We've already calculated them up above, but let's just go ahead and look at them again. This time I'll call this means, and we'll look at these using the t-apply. And so we have for our environment up here, let's remind ourselves, and actually let's go ahead and fill that in because I hadn't loaded the data yet. There it is. So this is plain risk and we're wanting to look at the scores, we want to look at those separated out by view. And we want to look at the means. So I've gone ahead and loaded those in. Let me actually go ahead and print them out here in my little notebook. So there are the individual means. So if I wanted to set up the contrast now, let's go ahead and do that. I'm going to put in another code chunk. And let's go ahead and calculate contrast. So I'm going to have my first contrast, I'll call it contrast 1. I'm going to have contrast 1 be the means for individualist minus the means for hierarchical list. So that's the first mean minus the second mean. Contrast 2 is going to be the means of individualist minus egalitarian. And then let's go ahead and do all pairwise. This will be the means for the mean for the hierarchicalist minus the mean egalitarian. And if I want, I could even do this. I could say contrast and put them all together in a single vector. And let's go ahead and look at that. All right, and oh, I don't like those labels that it put on. It kept the labels from my groups. So let me go ahead and on-name this. All right, there we go. So this 2.04 is the contrast 1. That's the difference between individualist and hierarchicalist. The 14.03 is individualist and egalitarian, and notice that's the largest one. But we also have a pretty large one of 12, the difference between hierarchicalist and egalitarian. So those are our three estimates of the parameter contrast. These are the contrasts based upon sample means instead of population means. Now, of course, anytime we have a statistic, the statistic has variation. That is, if we were to draw another sample, we would not expect to get the same values for our observations. So we're going to have variation of the contrast, just as we have variation of means, just as we have variation of standard deviations. Draw another sample, the contrast is going to be different, even if it's estimating the same population values. So if we're talking about contrast 1 comparing individualist to hierarchicalist, well, if you draw another sample from the individualist, hierarchicalist, egalitarian pool of individuals, you're going to get a different contrast for that comparison of individualist and hierarchicalist. So we have variation, and that's what's indicated down here in this formula, is that we're looking at the variation, in this case variance, or if I take the square out of the picture, it would be the standard deviation of the contrast. And since it's not the true standard deviation of the contrast, but rather an estimate, we call it the standard error of the contrast. So this is a scary looking formula, but let's go ahead and break it down and find out that it's not as bad as it seems. First of all, we have here a variance of our residuals, and that's just the mean square error that we obtain from an analysis of variance table. That is the variance of the residuals. The error is the unexplained part of our model, so this is the mean square or variance for the unexplained part of the model. Now note that in order to be able to use this MSE across all the different groups, you're assuming that you have equal variances. And that's just the same thing we do when we do an omnibus analysis of variance. We assume in the populations that the variance of the conditions are about the same. And so we're assuming here equal variances. Not equal variances in our sample data. Those are going to be different from one another. But rather, we're assuming that the variation of individualist and hierarchicalist and the variation of the egalitarians, that in that population, if we were to do a model in that population and calculate the residuals for all three of those conditions, that those residuals would be about the same. Actually, we say that they're exactly the same, but let's just call it close enough. So if we do not have equal variances, that formula is going to change a little bit. If I don't have equal variances, let me go ahead and clear my markings here and write something down. If we don't have equal variances, we have to bring that variance here that we're assuming to be equal. We have to bring it now inside the sum, so that what you would end up with is you would end up with a sum in which instead of bringing that squared epsilon inside, we would have to, or outside the sum sign, we'd have to have it inside, so that we would have a w squared k, and then we'd have an epsilon squared k, or sigma rather, sorry, sigma squared k, and then we would have the nk for the group. So this is the way it would look if we had separate little variances for each of the conditions. Now, if we do that, we're going to be restricted as to what kind of multiple comparison procedure we can use. So I'll talk about that later. And just to give you a heads up, we're going through the meaning of all these, but when we actually start working this out using the R statistical programming language, a whole lot of this is going to be done for us when we run these multiple comparison procedures. So I'm wanting you here to see how it all works. We're getting under the hood, but when we drive the car, we really don't have to be under the hood looking at what's going on under the engine. We can just push the pedal and move forward. And so we'll get to that point. All right, so let's go ahead first of all and focus on looking at variances, assuming that they're all equal. That is, the mean standard error will be the variance that we'll use. So earlier in another video, when we ran the analysis of variance table, here it is right here, the analysis of variance table, we got that mean square residual or mean square error, and that's 666.3. So we've already got part of our formula done. We just need to work out the other parts now. So let's look again at what those other parts are. It has to do with adding up weight square over sample size. So what are the weights that we're dealing with here if we're, say, comparing group 1 to group 2? So if I have a contrast in which I'm estimating the mean of 1 and estimating the mean of 2, what are the weights? The weights are 1, minus 1, and 0. 1, minus 1, and 0. So when I work out those weights squared, it's going to be 1 squared over the n of the first group plus minus 1 quantity squared over n of the second group plus 0 squared over n of the third group. Well, look at that a moment, and that can simplify. That could simplify to simply 1 over n1 plus 1 over n2. And that, in fact, if you remember back to your first statistics course, when you were looking at how to calculate the standard error between two means, what you did to get the standard error is you took the standard deviation, actually you took the variance over n1, the variance over n2, and if those variances are the same, the subscript can go away, and so that you can put a single variance on top. So this is the same formula that we had when we did two means, when we were first learning about such things as the two-sample t-test. That's how we were calculating the variance. So even though we've introduced this new contrast notation, nothing really much has changed here. So opening up the R notebook, let's go down here, add in another code chunk. So we could say that the variance of contrast 1 is equal to the mean square error, which remember here was 666.3. So the variance contrast 1 is 666.3 times, now I need 1, because that's, remember, our first contrast weight is 1, and 1 squared is 1. 1 divided by the sample size here. I need that. I don't have the sample size. So let's get the sample sizes for our groups. I'll put in another little code chunk here. And I'm just going to get a table of plain risk view. And that little table of plain risk view is just giving us the sample sizes. So for individualist, it's 50. So I have 1 over 50. And then I need 1, remember negative 1 squared is the next weight, and that's 1. So 1 over 98. And then I need the quantity of this. And that should do it for the variance of contrast 1. Again, to look at the formula, see the formula here. We have the sum of the weights squared over n, and then out in front we have the mean square error. So that is what I've done here. The 1 over n1 plus 1 over n2, and out in front is the mean square error. That's the variance of contrast 1. Let's go ahead, and I'm just going to copy that and make this real quick for the other contrast. For contrast 2, which is individualist and egalitarian, I just need to change that 98 to 77. And for contrast 3, I need to change the hierarchicalist 98 and 77 for egalitarian. So those are my 3 variances. And of course, if I take the square root of those, that would give me the standard error. So let me go ahead and make a little variance of contrasts, just like I did for the contrasts themselves. So we have, and I'll unname it, and so we have variance of contrast 1, variance of contrast 2, and variance of contrast 3. And I'll go ahead and get the variance, but then let's also go ahead and get the standard errors, which would just be the square root of the variance. So here are the variances, and here are the standard errors. So the standard error for my first contrast is about 4.49, just about 4.5. Not too much different for the next one, a little bit different for the third, 3.93 for my standard error. So that's how to estimate the individual contrast and the standard error. And hopefully you see where this is going. When you have a value for a statistic and you have the standard error for the statistic, and you know what the probability distribution is that can model the ratio of that estimate to that standard error, you can combine those all together and create a confidence interval. So that's where we're heading with this, and I'll see you to do that in the next video.